Good afternoon and welcome to the Harold B. Lee Library's House of Learning Lecture Series. Today we are privileged to hear from Professor Dallin Durfee from the Department of Physics and Astronomy. But first, we'll begin this lecture today with an invocation offered by Rob Steed, a senior majoring in English from Houston, Texas.
Our dear Father in heaven, we thank Thee for this day and for the chance that we have to be at this university to learn and to be instructed. And we thank Thee for the opportunity that we have at this time to hear Dr. Durfee's lecture and his presentation. We ask Thee that Thy Spirit will accompany us here, that we will be able to understand and grasp the concepts that He will explain. We ask that please bless us as we go throughout this day, that we will keep Thee in our minds, that we will be continually aware of our duties and goals as students and participants in this university. And for this we pray in the name of Jesus Christ. Amen.
Amen.
We are pleased today to have Professor Dallin Durfee as our featured speaker. His address is entitled Splitting and Recombining Atom Waves. We shall hear more from Professor Durfee in just a moment. The library sponsors three main lectures and lecture series: the annual Author Lecture, the House of Learning Lecture Series, and the Alice Louise Reynolds Women in Scholarship Lecture. This year, we are pleased to announce that Princess Martha Louise of the Norwegian royal family will deliver our annual author lecture on Thursday, the 6th of April, 2006, when she will discuss her new children's book, Why Kings and Queens Don't Wear Crowns. We invite you all to attend that very special lecture. Through these lectures, the library brings scholars and students together to engage in a civil discussion of ideas, and in so doing, the library contributes to building a learned community which fosters the faithful life of the mind. The House of Learning Lecture Series title is taken from the 88th section of the Doctrine and Covenants, verse 119, where the Lord instructs the saints to prepare every needful thing, even a house of learning. Because the library is the campus repository for the literature of all academic disciplines and scholarship, the library is well positioned to be considered BYU's House of Learning. The Harold B. Lee Library takes seriously its campus role as the intellectual heart of inquiry and knowledge, and is honored to provide this House of Learning lecture today. Now, about our speaker today. Professor Dallin Durfee earned a Bachelor of Science degree at BYU in 1994 and continued his education at the Massachusetts Institute of Technology, where he earned a PhD in physics in 1999. After leaving MIT, Professor Durfee held a postdoctoral research position at Yale, where he engaged in research on atom interferometry. Since returning to BYU, Professor Durfee has been involved in cutting-edge research, and he has authored nearly 24 scholarly, peer-reviewed articles and book chapters. We're delighted to have this young and accomplished scholar-scientist with us today. Ladies and gentlemen, please welcome Professor Dallin Durfee.
Thank you very much. It's a privilege to be here today. I love any opportunity I have to talk about, well, the things that I think are really interesting and drive my life outside of my family, of course. Today I'm going to be talking about splitting and recombining atom waves. And this is kind of a big topic to try and swallow in one presentation. So here we go. We're going to try. But first, before I dive into this, I'd like to just acknowledge a whole bunch of people that have helped me out and have worked with me. In particular, I'd like to point out that there's been a lot of undergraduates who've worked on this. And it's really undergraduate students who've done most of the work in my lab that I'm going to be leading up to in this talk. Also, before we get started, I have to give you a quick disclaimer, all right? I am not presenting quack science. This happens to me all the time when I give a lecture based on quantum mechanics. What I will discuss is the result of something called quantum mechanics. And if you aren't familiar with quantum mechanics, it'll sound really counterintuitive. But quantum mechanics has been tested in many experiments. And the strange things I tell you are based on ideas found in any good modern physics textbook. Someday we'll find a theory that goes beyond quantum mechanics. It's inevitable that quantum mechanics is wrong. But until then, quantum mechanics is the name of the game. And when we finally do find another theory, chances are it's going to be even weirder. All right, so live with it. All right, now, before I can talk about interfering atom waves, I need to make clear what a wave is and what waves do. All right, so what exactly is a wave? Well, a wave, in a sense, is a way that energy can transfer itself from one place to another. For example, if you study waves with me in Physics 123, you'll be issued a slinky. And what you thought was a lot of fun will turn into hard homework problems. All right? But the basic idea is here, if I whack the end of this slinky, you'll see a little compression wave bounce back and forth. What's happening is, as I push on one piece of the slinky, it compresses that piece. It doesn't want to be compressed, it wants to stretch out, so it pushes on the piece next to it and compresses it. Well, it doesn't want to be compressed, so it pushes on the piece next to it. And that way the energy travels down the slinky. Another example of a wave is my voice. As I talk to you, my mouth is emitting energy, and that energy is reaching your ears. All right? It's not the actual air that's getting to you, it's the energy. That way you can hear me without actually having to smell my breath. That's one of the wonderful things about waves. Now, let's talk about some of the properties of waves. Imagine that I have a stereo, and I play a pure tone, a pure frequency through both speakers. All right? Right next to the speaker, I've got the speaker cone that's moving back and forth, and it's pushing the air, it's compressing the air. So right next to the speaker cone, you'll see the pressure of the air go up and down in time, and that's what I'm representing here. And that pressure, that little pulse of pressure, then travels outward. All right, now imagine you're sitting right between two stereo speakers, and they're both doing exactly the same thing at the same time. What you hear then is the combination of both of those sound waves coming from both speakers. So you hear the sum of those two. You add them together, and you get an even bigger wave. All right? But what would happen if I'd accidentally wired up one of my speakers backwards? I flipped the wires. Well, now, when this speaker is moving that way, the other speaker is moving this way. And you can see the pressure waves are out of phase, we say. This one's going up when that one's going down. So when these two waves reach your ear, you add them together, and they just cancel each other out. And you hear no sound. Now, if you've ever wired up your stereo system backwards, you probably didn't hear no sound because there's all kinds of idealizations going on here. In a real stereo, in a real room, you'll also get sounds that don't come straight from the speaker, but ones that maybe reflect off of a wall or a ceiling and come to you. But you will notice, if you sit right between the speakers, there's a lot less vivacity, there's a lot less volume to the sound. All right? Now let's imagine another scenario. Imagine that my speakers are wired up correctly. They're both doing the same thing at the same time. But imagine you're sitting in a place which is closer to one speaker than the other. Well, the speaker that's further away, its sound wave has to travel further, and it takes a longer time before it reaches your ear. And as a result, the wave is shifted a little in its phase. It's delayed a little. So now if I'm sitting in just the right position, it turns out I can actually have those two waves cancel out at my ear, even though both speakers are exactly in phase. All right? So let's do a little demonstration of that, shall we? I've got two speakers here. I'll turn up the volume. And what I want you to do is close one ear and then lean side to side and listen to how the volume changes. Who can hear that? All right. So this phenomena, where waves can add together or they can cancel out, is known as interference. And interference is something that waves do. All right? Here's just a little animation of what just occurred. I have one speaker, and it's emitting these waves. I have another speaker that's emitting waves. If I add these two waves together, I get this. There are places where the two waves cancel each other out and not much happens. There are places where they add together and I get a lot of sound. Now if I come over here and detect what places there's lots of sound and what places there's not, that is known as an interference pattern. All right, waves interfere, they form interference patterns. Ocean waves can do the same thing. All right, imagine that I have some waves that are traveling. There we go. Imagine that I have some source of waves that are making ocean waves travel kind of up and to the right here. All right? Now let's turn off that source and turn on another source, which is traveling up and to the left. What happens if I have both sources on at the same time? Well, before I show you that, I'm just going to show you another little video where I have the left going wave, and then we're going to fade over to the video of the right going wave. All right? And it'll just fade back and forth. Now if I stop, we're seeing kind of both videos overlaid on top of each other. And you'll notice along this line right here, wherever the left going wave has a trough, the right going wave has a trough. Wherever the left going wave has a peak, the right going wave has a peak. All right? So along this line you expect really big waves because both contributions are doing the same thing at the same time. If you move over a little bit, you look right here, look, the left going wave is a trough, but the right going wave is a peak at that point. So when I add those two waves together, they're going to cancel out. Up here, the right going wave's a trough, and the left going wave's a peak. So all along this line here, the waves are going to cancel each other out. So let's see what happens when I add these two waves together, and there it is. If you're on a beach somewhere, and these waves are coming in, if you're sitting right here, you'll say, oh boy, surf's up, a lot of big waves. If you were planning on going surfing because you heard that there were some big waves being generated on the ocean, but you happen to show up on this piece of beach here, you'd be disappointed because the waves will cancel out. There's nothing there. All right? Now, another type of wave is light. Light from a laser pointer, the light that's coming and projecting this image on the screen. Light is also a wave. Now, how do we know that light's a wave? Well, if I look at ocean waves, I can actually see these wavy things moving along, right? But with light, the spacing between these waves is really, really small. And the rate at which they oscillate is really, really fast. So you can't go and directly measure the waves in a light wave. So how do we know that light is a wave? Well, what do waves do? They interfere. So I can do an interference experiment. For example, I can take a laser, split it into two pieces, and send those two pieces together. Just like our ocean waves colliding together, we should see stripes. We should see places where the two waves add together brightly and two places where they cancel out. All right? So that's what we should see. What do we actually see? Let's go over to a little laser I have here, and I'll show you. All right? So turn this laser on, and what you see are a couple spots. All right? I have a beam of light. I have two beams of light, but I'm blocking one of them. Let's see what the other beam of light looks like. All right? It looks like that. It looks a lot the same, doesn't it? But what if I put the two of them together? Voila! I see interference. And it turns out the spacing between those interference fringes depends on the angle between the two beams. So if I make small changes to the relative angle of these beams, I can make the interference fringes get bigger and smaller. So there you have it. So the verdict is in. Light is a wave. All right, and it turns out when I take a beam of light and split it and recombine it to see an interference pattern, the device that I've made is called an interferometer. And I told you I was going to talk about interferometers, but I didn't say I was going to talk about light interferometers. I said I was going to talk about atom interferometers. So we better move on, all right? Well, before we move on, we have to put a little history behind this. Back at the end of the 19th century, there were a lot of people who said that physics was done. And there are people who think that today, too. But then and now, there's some things you can't just really explain very well with the models of physics. So they had Maxwell's equations, they had Newton's laws, and they thought that that's all there was. But there were some puzzling inconsistencies, and one of which had to do with blackbody radiation. Blackbody radiation is the light that something gives off when it gets hot. You turn the burner on your stove and it starts to glow, that's blackbody radiation. You turn on a light bulb, current flows through a filament, it heats up and glows, that's blackbody radiation. The sun, it's big, it's hot, and it glows, that's also blackbody radiation. All right? So, back at the end of the 19th century, experimentalists were measuring the different colors that came out at different temperatures. Well, you take the so-called understood physics that they knew at the time, and you predict the entirely wrong thing. And nobody understood why. Well, a guy by the name of Max Planck started thinking about this, and he took a kind of interesting approach. What he did is he first found an empirical formula that fit all the experimental data without wondering about what the physics was behind it. And then he asked himself, what do you have to do to derive this formula? All right? And what he found was that in order to derive his equation, he had to assume that the energy in the radiation had to come in packets. The light coming out in blackbody radiation came in little energy packets. Now, if you think of an ocean wave doesn't look like little packets of anything, does it? It's a big continuous thing. So, what kinds of things come in packets? Well, particles. You know, a marble. It's as if the light are little BBs shooting through the air. So the conclusion then is that light is a particle. Light is like little BBs moving through the air, little packets of energy. But wait a minute, we already just proved that light is a wave, didn't we? So we've got a dilemma. But before we solve this dilemma, I need to introduce you to a man by the name of Albert Einstein, if you've never heard of him before. Now, what did Einstein win his Nobel Prize for? A year ago, if I'd asked you, most of you probably would have said relativity. But since, as you all know, last year was the World Year of Physics, celebrating the 100th anniversary of the year that Einstein published his 3 most famous papers, you probably saw something on PBS that told you otherwise, right? The thing that Einstein actually won his Nobel Prize for was a phenomena known as the photoelectric effect. And the photoelectric effect is basically a phenomena where I shine light at a piece of metal and electrons come shooting out. And once again, experimentalists did different things. They changed the color of light on the metal, they measured the energy of the electrons coming out, and guess what? The classical theory did not describe what they were seeing. So Einstein looked at this problem and he thought long and hard about it, and he came up with an amazing conclusion. An incredible conclusion, so incredible that they gave him a Nobel Prize for it. And this is Einstein's amazing statement that won him a Nobel Prize. Planck was right. All right? Light really is like little particles. All right? And it turns out then that the way we reconcile wave experiments where we prove that light's a wave and other experiments that prove that light is a particle is that in fact light acts as both. There are times when it behaves as a wave and times that it behaves as a particle, which is kind of weird. We call this the wave-particle duality. All right? Now, soon after this, a man by the name of de Broglie was sitting and thinking, and in his journal he says that this idea came to him like a bolt out of the blue, and this was his idea. If light, which we thought of as waves, behaves as a particle, then maybe things we think of as particles behave as waves. And very soon after he made this conjecture, a couple experimentalists by the name of Davison and Germer were shooting electrons at a little piece of nickel, and they saw a diffraction pattern. They had never heard of de Broglie's conjecture, unfortunately, so they had no idea what it was. But eventually they found out about de Broglie's work and said, aha! This is true, we've seen it. Electrons behave as waves. All right? And it turns out that atoms behave as waves too. And in fact, people have done interference experiments with things as big as molecules of 60 atoms. It turns out it's harder and harder to do this as things get bigger and bigger, but the supposition is that everything behaves as a wave. This table, you and I, the planet Earth, are all described by a wave function. All right? Here's just a little, how do we tell if atoms are really waves? I guess I blew the punchline there. We look for interference. Here's a picture of interference that I took as a graduate student. What we did is we took two little clouds of really cold sodium atoms inside of a magnetic trap. Then we turned off the magnetic trap and let these little puffs of gas expand into one another. And after some time, we measured the density of atoms in a plane. And this is a plot of that density. And what do you see? Interference fringes. So indeed, atoms are waves. And if atoms are waves, I can make an interferometer out of atoms. Okay, so matter is made of waves. What good does that do us? Well, it turns out you can do all kinds of really cool experiments and make all kinds of cool devices because atoms are waves. And here's just one example. One example is a Sagnac interferometer. Now, a Sagnac interferometer is a way to use interference to measure rotation. And people have been making Sagnac interferometers for some time using light. And in fact, laser Sagnac interferometers are used today to help navigate airplanes and missiles and submarines. All right? And the way that it works is, imagine that I have a beam of light, and I know this light is really a wave. It's something oscillating back and forth. I send this light to a thing called a beam splitter. And a beam splitter is just a mirror that lets a little bit of light through. So this beam splitter lets some light through and reflects some light. So now I've split my laser beam in half. Half of the light will go up here, hit a mirror, and be redirected down to a second beam splitter. Half of the light will come, hit this mirror, and be then redirected to the second beam splitter. Now if I look, the light traveling this path, when it hits this beam splitter, some of it will go through the beam splitter and some of it will reflect. The light that takes this path, some of it will go through the beam splitter and some of it will reflect. So what I get coming out here is a sum of light that went that way and light that went that way. So I get a little bit of wave that went this way and a little bit of wave that went that way, and they add together to make a bigger wave. But if I look at the light coming down here, it turns out that the light going that way and the light going that way get phase shifted when they reflect off of these different devices, such that they're out of phase with one another, and when they add together, you get zero. They cancel each other out. But now, what happens if my whole apparatus starts to rotate? Well, the light doesn't care that the experiment's rotating. It still travels a straight path. So what happens if I start to rotate the whole experiment, by the time these two bits of light get together on this beam splitter, the beam splitter will have moved. So now this light has to travel less distance than that light. And that causes a delay in the arrival time of the two bits of light, which causes a phase shift. So now this beam, the contribution from the upper path, is not exactly in phase with the bit from the lower path. They don't oscillate up at exactly the same time anymore. So when I add them together, I don't get quite as big a wave anymore. And then down here, if I look at the light coming in this direction, they don't totally cancel each other out anymore, and I get a little bit of light coming out this port. So if I put a little photodetector here and measure how much light comes out in that direction, I can infer then how fast my experiment is rotating. And it turns out you can make a very sensitive gyroscope that way. Well, you can do that with a laser beam. You can also do it with atoms. So how do you make an atom interferometer? Well, you need certain things in order to make an interferometer. For the light interferometer, we had a source of light, a laser. We had a beam splitter to split the laser beam in half. We had mirrors to take the two halves of the wave and bring them back together again. And we had a detector to see how much light came out in one direction versus the other. So how do we do that with atoms? Well, in all the experiments I've worked on, our source of atoms has been an oven. We heat up some chunk of metal, and we heat it up enough that some of the atoms start to vaporize. And then some of that vapor escapes through a hole in the oven and makes an atomic beam. How do I make a beam splitter for atom waves? Well, it turns out we use a laser beam. How do we make mirrors? We also use a laser beam. And to detect what port the atoms come out in, we use a laser beam, plus a photodiode to detect the light that the atoms scatter. All right? So now how do I make a mirror or a beam splitter with a laser beam? I'm about to explain that. Here we've got an atom. That's not really what an atom looks like, but that'll represent an atom. And here I have something known as an energy level diagram. It turns out quantum mechanics tells us that I can put energy into an atom, and it can store that energy. but the atom can only be in a certain allowed energy states. I can't put an arbitrary amount of energy into the atom. So I've depicted two of those allowed energy states with lines here. The lower line means a lower energy state, and the higher line means a higher energy state. And this little dot here says that the atom right now is in the lower energy state. All right? Along comes a photon, and the atom absorbs it. A photon, by the way, is what we call a particle of light. So the atom absorbs this little particle of light. What happens? Well, that little packet of light carries energy. So the atom absorbs that energy and goes into a higher energy state. But the little particle of light also carries momentum. So when it absorbs the light, it gets a little recoil kick. And now my atom's flying along. All right, I had to stop it on my overhead here because I didn't want it to fly off the screen. But imagine this atom is just flying away now. All right, so I can deflect an atom simply by shooting light at it. What happens now if my atom's in the excited state and it's flying away? What happens if another light particle comes along? Well, here comes my light particle. Well, the atom can't absorb its energy anymore because it's already in the higher energy state. But Einstein figured out that what the atom can do is it can feel the presence of that photon, and that photon can tickle the atom and make it give off its energy. So that photon will tickle the atom, force the atom to go back into the lower energy state, and it does that by emitting a second photon, which is identical to the one that tickled it. And incidentally, this is the process that makes lasers work. All right, so now that photon carries off the energy that the atom had, but it also carries off the momentum we'd given the atom, and so the atom will come to a stop again. All right, so that's how I can make a mirror. I can make an atom deflect, and then I can stop it again. If I want the atom to go that way, I send a laser beam, and I deflect it that way. If I want it to stop, I send another laser beam in the same direction, and I can get it to stop. Now, how do I make a beam splitter? Well, it turns out I've only described one of the things the atom can do. When this light particle comes along, it can absorb the light particle and recoil away. But the other thing it can do is totally ignore the light and let it go by. And it turns out if we adjust the intensities of our lasers just right, we can set up a situation where the atom actually does both, where half of its wave thinks it's absorbed a photon and recoils away, and the other half of its wave thinks it hasn't absorbed the photon and continues along its way. So here's a diagram of an experiment I worked on just before I came to BYU that measured rotations using this Sagnac effect I described earlier. And the way it worked is we'd send a beam of cesium atoms in, and that's represented by the black line. The black line represents a cesium atom in the lower energy state. Then we have a laser beam that the atom interacts with, and half of its wave thinks it hasn't absorbed light, and the other half thinks it has, goes into the excited state and recoils away. At this point, we have another laser beam which is twice as intense, which assures that with near 100% probability, this atom in the part of the wave in the ground state, in the lower energy state, absorbs a photon. And this piece up here in the higher energy state is induced to emit a photon with nearly 100% certainty. So this one now gets a momentum kick, and this one loses its momentum kick. So now they fly towards each other, and right where they're overlapping, we have a third laser beam, which allows these two states to interfere and mix. All right? So now all you have to do is detect which way the atoms are coming out, and it turns out detecting which way they come out is the same thing as detecting what state they're in, whether in the lower or the higher energy state. So here, there's a lot of data on this plot, but if you just look at the black line here, this black line is a plot of the number of atoms per second coming out in the excited state as a function of the rate at which the apparatus was rotating at. And so you can see, by measuring the number of atoms coming out in the excited state, you can figure out how fast the apparatus is rotating at. All right? Here's a picture of the apparatus I worked on. It's basically a big vacuum chamber because the atoms we can't let them collide with air. So we suck all the air out. This little piece of tin foil covers an oven where we heat the cesium up. The cesium beam flies through this vacuum chamber, and you can see kind of 3 places where our laser beams come in and interact with the atoms. Now, how good was this atom interferometer gyroscope? Well, imagine that I draw a line all the way across the country. Now I'm going to let that line rotate very slowly at the smallest rotation rate that our gyroscope could detect. All right, so here's a real-time enactment of the type of rotation rate our interferometer could detect. Here we go. How fast is that moving? Not very fast. In fact, the type of rotation we could detect would have this line, have the end of this line sweeping about half the thickness of my pinky per second. And my pinky is very small compared to the state of California, so that's why it appears like this line isn't moving. So it's a very sensitive device. It's the most sensitive gyroscope ever built. Now, if you have a really sensitive gyroscope, it turns out there's some cool, fun things you can do. It turns out there's this weird thing that Einstein's general relativity predicts called the gravitomagnetic force, which causes something called the Lenz-Thirring effect. Now, if you've seen on PBS a show on Einstein's general relativity, you probably know that the way that Einstein describes gravity is he says that massive objects actually bend space-time. They warp it, and that makes stuff come towards it. All right, so this grid here represents space-time. If I throw a big planet or a big star in the middle here, it'll distort space-time. Gravity distorts space-time. All right, but now imagine this planet, say Earth, for example, is rotating. It turns out there's a higher order effect, and what happens is this rotating massive body can actually swirl based space-time. So if you were to look at the stars and watch how the stars appeared to rotate, you know it's not really the stars that are rotating, it's the Earth that's rotating, right? So you can calculate how fast the Earth is rotating by looking at the stars. But now imagine you make a really, really good gyroscope and measure how fast the Earth is rotating with your gyroscope. Well, it turns out, if you do this very, very precisely, you'll find that the two measurements disagree with each other by a tiny amount. Because the stars are far away from the Earth, but the gyroscope is here where space-time is being curled up and spun up by the rotating Earth. So there's an experiment with a gyroscope up in space right now that's trying to measure this. But, you know, if you had an atom interferometer that was 10 times longer than the one I described, you could beat those guys in a heartbeat. So that's something fun you can do with a gyroscope. Now, the atom interferometer we're building in my lab right now uses a slightly different configuration for reasons which I don't have time to explain. Instead of using 3 laser beams, we use 4 to split and recombine our atom beam. Here is part of the experiment. We're actually building pieces of it in different places. Here's the vacuum chamber where all our optics are going to sit and our atoms will fly through there. Here's one of my undergraduate students working on it. He's also been building an ultra-stabilized laser that's on another table, which will be part of this. And we have a couple other students building a cooling laser, and a couple students trying to temperature stabilize this oven better and make our atom interferometer more precise. So there are a lot of parts being built, and it'll eventually all end up, all these pieces, once they work, they'll collect around this big chamber here. What is our atom interferometer going to be good for? Well, one of the things it'll be good for is it'll represent a better atomic clock. By better, I mean more precise. All right, this is the very first atomic clock that was used as a national time standard. And atomic clocks have made a lot of interesting things possible, like the global positioning system, for example. There's a lot of interesting things you can do with an atomic clock. To explain how an atomic clock works, the best way to do that is to teach you a dance. It's the Ramsey's method of separated oscillatory fields dance. But unfortunately, to interpret this dance, you have to know a lot more math and physics than I have time to describe today. So we'll forego the dance. But if you ever take an advanced atomic physics class from me, I will teach you the dance of the atomic clock. Now, if you have a really good atomic clock, there's some fun things you can do. For example, you can do tests of special relativity. Einstein's special theory of relativity says that if I have 2 twins, I leave one on Earth, I put one on the Starship Enterprise and fly him far out into space, traveling nearly the speed of light, and then back again. When the space-bound twin comes back, he'll find that the twin that stayed on Earth is a lot older than him. Time passed more slowly for the one who is moving quickly. Now, we've tested this theory, doing such things as taking unstable particles, and we know how long it takes for them to decay on average, and we accelerate them, going really fast. Now, in the particles reference frame, they still decay at the same rate they normally would. But we observe a longer time before they decay. And we can calculate how long it should take from Einstein's equations, and it turns out they're correct. But Einstein's relativity should not just apply to things moving quickly, it should also apply to things moving at reasonable velocities. For example, if I take one of the track team at BYU, when he's running a meet, he should be aging just a little bit slower than he does when he stands still. All right? But it's such a small effect that you don't notice it. But it should still be there. And it would be neat to go and see if you could test that and see if Einstein's equations really do meet up with Newton's equations in the way we expect them to. Well, if he were carrying an atomic clock, maybe we could figure this out. All right? And it turns out that the apparatus we're building, if it works the way we predict it will, we should be able to see these little changes in the rate of time, even if our apparatus is only moving about 1 meter per second. All right? And that's something that's totally achievable. Einstein also predicted, with his theory of general relativity, that if I were to put a clock on top of, well, a clock on the ground and a clock on top of the Irene Science Center, because they're sitting in different places, the influence of gravity will change the rate at which they run. And the clock on the ground will actually run a little slower than the clock on the top. Now, experiments have been done using much greater distances, and they've found tiny, tiny effects. Our clock, if it works the way we expect it to, should be able to actually measure this precise scenario right here. All right? Now, as I showed you, you can make a gyroscope with an atom interferometer. You can also make an accelerometer. And our device ought to, in addition to acting like a clock, we should be able to configure it to operate also as an accelerometer and a gyroscope, which is really useful for navigation. If you're flying an F-15 over Iraq, or I guess Iraq's old news now, right? The next country that we choose to invade, maybe their dictator is going to jam the GPS signal. We rely a lot on GPS, but it turns out it's a really weak signal. And for about $6,000, there was actually a web page up once where you could pay $6,000 and buy the technology that you needed to basically jam GPS around the entire border of Iraq. This came up during the Iraq War. So it's a very fragile technology. So if you're flying in an F-15, you'll be comforted to know that there's an inertial navigation with accelerometers and gyroscopes that takes over when you lose the GPS signal. If you're on a submarine, when you're underwater, you don't pick up GPS. Furthermore, there are no landmarks underwater. You can't see underwater. So submarines rely almost exclusively on accelerometers and gyroscopes to basically feel how they're moving and figure out where they are based on the forces that they felt as they were moving around. If you don't have a good accelerometer or a gyroscope, things like this can happen. So there's some practical applications of our work as well as fundamental ones. And the one last application that I want to point out is a search for changing constants. Now, according to the Standard Model and Einstein's general theory of relativity, the constants are constants. You write them down and you live with them forever. But there's some new theories of physics that people are wondering if maybe this is the next step beyond our current model of physics, and some of them allow the constants to change. Now, there was a big stir a few years ago when some people looked at the light coming from very distant objects out in space, light that had been traveling for over 1 billion years. And they found that the wavelength of that light is a little bit different than the light that would be emitted by the same types of atoms here on Earth. And their conclusion was the constants must have changed a little bit over the past billion years. Well, it turns out these measurements are pretty noisy. And most of the people who look at the raw data are not as confident as the people who publish the paper that they've really seen what they think they're seeing. But this is of paramount importance if we want to discern between different perspective new theories of physics that'll take us beyond what we know today. So we'd like to maybe do an earth-bound experiment where we measure these things in the laboratory. And the way you do that is you make an atomic clock, and then you make another atomic clock, and you use 2 different elements in your 2 clocks. And you compare how the relative frequencies of those 2 clocks drift in time. In our experiment, we actually have it set up so that we can put 2 different elements in the same clock and have 2 different laser beams traveling over the same path, so that a lot of the noise and things that might wash out your signal will cancel out when we measure the relative frequencies of the two. So we think our device will be really fabulous for these types of measurements. Anyway, that is, I think, all the time I have. So I guess at this point we take questions. Thanks again for having me.